All right, imagine trying to do high-level math, but every single number you work with is completely trapped inside a physical shape. Sound exhausting? Well, welcome to this explainer, where we're going to dive into a massive paradigm shift from the 17th century, the formalization of mathematics. We are going to look really closely at how two absolute geniuses, René Descartes and Pierre de Fermat, completely blew up our understanding of space. They took humanity away from literal physical geometry and pushed us into the boundless, wild world of abstract algebraic symbols.
So, I want to start by asking you to really imagine that world where math is completely bound by physical shapes. Think about the classical Greek tradition. Back then, arithmetic, which is all about discrete numbers, and geometry, which deals with continuous shapes and magnitudes, were kept strictly, absolutely separated. So how did we eventually break out of that restrictive box? How did humanity actually create the fluid, symbolic, data-driven math that literally builds our modern world? To understand this huge leap, we have to talk about classic algebra. For millennia, this system severely limited European mathematics. It was basically a mathematical straitjacket. In classic algebra, equations were treated as literal physical dimensions. If you wrote down a squared term, it absolutely had to represent a physical two-dimensional area. A cube term? That was a physical 3D volume. Because of this rigid rule, generalizing values or modeling complex motion was incredibly difficult. But then, analytic geometry burst onto the scene and changed everything, letting mathematicians use abstract coordinates and easily manipulable algebraic symbols instead of having to draw out physical shapes every single time.
Now, this formalization of math didn't just happen peacefully in a vacuum. Oh no, it was driven by a massive clash between two brilliant minds with completely opposite philosophies and lifestyles. On one side, you have René Descartes, the famous, highly competitive superstar academic and systematic philosopher. And on the other side, Pierre de Fermat. He was a cautious, secretive magistrate at the Parlement of Toulouse who treated this world-changing mathematics almost like a private weekend hobby.
Just think about the timeline of how fast this happened. After those ancient Greek traditions dominated for centuries, things suddenly accelerated. In the 16th century, François Viet introduces symbolic logistics. He starts using vowels for unknown variables and consonants for knowns. But the real explosion happens right in the middle of the 1600s. Descartes drops his landmark essay La Géométrie in 1637. Meanwhile, Fermat had been working independently in the shadows since 1629, but being so secretive, his groundbreaking work wasn't even published until 1679, long after he had died.
Descartes, as you might guess, had swagger. He was supremely confident. He famously declared that any problem in geometry could easily be reduced to such terms that just knowing the lengths of certain lines is enough to solve it. I mean, that perfectly illustrates his ambition, right? He wanted to systematically colonize all of geometry using algebra. He firmly believed we didn't need complex multidimensional physical models anymore. Everything could just be boiled down to simple lengths of lines on what we now call the Cartesian coordinate plane.
And to do this, Descartes had to break the rules. Specifically, he shattered the traditional homogeneity rule. Before him, traditionalists like Viet insisted that an expression like a squared had to be an area, and x cubed had to be a volume. You could not mix them without breaking the laws of physical reality. But Descartes? He brilliantly argued that algebraic terms of higher powers could simply be divided by a unit, like the number 1, to step them down. Just like that, he freed mathematics from physical dimensions entirely. Suddenly, a square didn't have to be a box. It could just be an abstract length. It was a total game changer.
But look, for all his innovation, Descartes was still incredibly rigid in his own ways. He created this incredibly strict taxonomy for what was acceptable in his new mathematical universe. He only allowed what he called geometric curves. These were algebraic curves you could generate with precise, continuous mechanical movements, like drawing with a compass. He entirely rejected what he called mechanical curves, which today we know as transcendental curves, labeling them mathematically intractable and inexact. Basically, if it didn't fit his tools, he didn't want anything to do with it.
A prime example of Descartes' blind spot here is the quadratrix. This is a gorgeous, complex, transcendental curve formed by the intersection of a steadily rotating radius and a steadily dropping horizontal line. But because you can only pinpoint specific spots on this curve using classical division methods, and you can't trace every single point in one continuous sweeping motion, Descartes' rigid rules just banished it entirely. He literally refused to use it.
Which brings us to a really fascinating mystery. How do you solve incredibly complex problems, like finding the exact slope or tangent of a curve at a specific point, if you refuse to play by Descartes' strict geometric rules? Descartes himself used these complex, normal-line physical constructions based on intersecting circles. But his rival Fermat? He took a much more abstract, almost magical approach.
Working entirely in secret, Fermat developed this brilliant, totally rule-bending method called adequacy. Instead of messing around with physical compass constructions, Fermat brought in an approximate algebraic parameter that he called E. This E was essentially an infinitesimal. It's a quantity so impossibly small that it's basically a ghost, barely there, but not quite zero. He would set up an equation saying the function of A plus E is approximately equal to the function of A.
This concept was basically a three-step mathematical magic trick that ended up paving the way for modern calculus. First, Fermat would introduce this incredibly tiny element, E, into his polynomial. Second, he'd do the algebra, dividing everything by E to clean up the equation. And then, step 3, the ultimate sleight of hand. He would just neglect E at the very end. He treated it as if it were exactly zero. And poof, just like that, the slope of the tangent reveals itself algebraically.
Now, as you can probably guess, this did not go over well with everyone. Philosophers, especially Descartes, were absolutely enraged by this illogical sleight of hand. They were like, you can't divide by E and then suddenly claim E is zero. But the danger actually went way deeper than just academic rivalry. Fermat's atomistic math, this idea that continuous lines are made up of indivisible, infinitesimal discrete units, was incredibly controversial. It directly clashed with established 17th century Catholic dogma, specifically doctrines around transubstantiation. And remember, Fermat was a cautious judge living in a politically volatile France, fully aware that people were literally executed over theological disputes. So yeah, it's no wonder he kept his work largely unpublished.
When you really compare these two guys, the contrast is absolutely striking. You've got Descartes, the famous system builder with strict rules, demanding that algebraic geometry stay grounded in continuous, constructive physical motions. And then you have Fermat, the cautious judge, quietly using highly controversial analytical hacks, these infinitesimals, to solve complex problems, completely ignoring the limits of physical construction.
But here is the best part. Ultimately, history didn't pick just one of them. It smashed their genius together. The synthesis of Descartes' universal coordinate geometry, the grid, and Fermat's fluid, rule-breaking infinitesimal methods gave us the complete algebrization of mathematics. Later on, Newton and Leibniz would take Fermat's little e and formalize it into rigorous differential calculus. This synthesis forever transformed the natural sciences and gave us the incredible tools we use today to quantitatively model the entire universe.
Which brings us to the end of our explainer today. We've seen how stepping away from tangible shapes and into the realm of pure abstract algebra fundamentally changed the course of human progress. So, I want to leave you with this provocative thought. If translating classical geometry into abstract symbols unlocked our modern understanding of physics, engineering, and the universe, what undiscovered realities are we staring at right now, just waiting for someone to invent a completely new mathematical language to unbox them?